Okay, so today we're going to talk about Future Facilities has done in sort of partnership or working alongside KO Data and I think JCA Engineering. The project was, and I need to get the words right because I guess they matter, is 100% free cooling wholesale colocation facility, the UK's first to match that description. So I guess a good place to start is just a bit of background as to how that project came about.
Well, from our perspective, from my perspective, we were approached by JCA Engineering. They were interested in our software and its capabilities. So they tried it out, and they were obviously engaged with KO Data, and they wanted to understand what they could achieve with our software Six Sigma DCX. I think when it came to the modeling, the external modeling that we did for them, or that the project required, that needs a bit more of an experienced hand. So we ended up doing the external modeling. We worked collaboratively with them for both internal and external, but we did the external modeling, and then we worked perhaps more collaboratively with them for some of the initial internal designs as well. Yeah, I think that explains it. I think Paul Finch is one of the head guys at KO Data, and I think he's familiar with the CFD technology aspect, and obviously the one of the objectives of KO Data was to be an energy efficient facility. So the CFD aspect of that and the science behind it all ties up well.
Okay, and in terms of the actual sort of application, as far as I understand it, was to do with indirect evaporative cooling, the sort of the suitability of that, and maybe you can talk a little bit about the actual sort of implementation side, how it helped the implementation of installing that solution, and also I guess before that, this sort of it could predict the likely or the performance of that. So yeah, a bit about how it helped that solution be decided upon and then implemented.
Yeah, well, I think the decision had been made in terms of going for the free cooling option only through the indirect evaporative coolers, and really I think it was believed it could be done, but the risks when you're relying on it exclusively without doing any testing, I guess you'd say that there were risks associated with that, and the modeling was to really prove that the site could operate without mechanical cooling, even on in the worst case conditions, so on the hottest days. I mean, what our software actually does, it's a 3D. It provides it provides a 3D model of either internally in a white space or an external site design. So you create the site layout or the data hall layout, and then you can put a lot of objects into that data center or the site. So the servers, the cooling equipment, generators if you're doing an external design, and then you can well, all of those bits of equipment have got characteristics associated with them so that they behave like the real life objects, and then with all of those objects in place, you can simulate the environment, and that simulation brings all of the devices together and lets them interact as if they would in real life. So that's what the Six Sigma DCX software does that we produce.
So in terms of CFD, computational fluid dynamics, I guess it's more associated with sort of wind tunnels and modeling, I don't know, aircraft in Formula One, but where's it sort of sweet, or what does it bring to a data center environment?
Yeah, so all right, so yeah, the CFD aspect is traditionally associated with things like Formula One and aerospace, but it's quite possible to use it for an array of things, and what we're doing is an application specific version of the CFD, and I've actually started calling what we're doing as CFD plus, and the idea being that we're evolving a basic or a general purpose CFD tool so that it fits an application specifically, such as data centers, and that means we can remove some of the unnecessary considerations that a general purpose CFD tool might offer, and that you might have to think about, but we can then augment the CFD with other aspects that are relevant to the model. So object-based characteristics, such as I was just talking about, so servers in the data center, we can associate those individual servers with certain power outputs and certain fan flow rates, and you can create their geometry so they represent the real thing. And actually, we've got a library of thousands of those items, so people can just drag and drop them in, which is kind of an example of how the application specific side of it makes it a bit easier for users within that industry, because the tool is tailored for those users. It looks at control systems, so it can emulate the control systems found within the servers themselves, but also within the controls, within the cooling units and the cooling infrastructure in the building. So not only have you got CFD running and you've got kind of smart objects in there, but you've also got them interacting with one another or against one another, or however they're going to operate in real life. That whole dynamic is simulated. And it's being continually improved. We've been around for over 15 years, and the models are becoming more and more comprehensive day by day. We're always looking to improve things, and we work closely with the industry to offer relevant solutions and features that are needed.
And I'm guessing, I'm not trying to be facetious or stupid, but I'm guessing it's pretty accurate, otherwise people wouldn't use it. So what you simulate then is borne out by the reality, so you can build with confidence, or are there elements where you have to reuse the CFD as you actually go from the virtual to the physical world, or is it pretty much what you've mapped in the virtual world then happens physically?
No, the science, so the maths part of it is very accurate. The software is capable of being very accurate, but the models are a result of the data that they've been built from and how they've been put together. So I guess you can get great results from CFD. It's possible also to get misleading results from CFD, and a modeler does need to appreciate, so someone using the software does need to appreciate the significance of the data that they've got available to them, and also any assumptions. So when there's data not available, so in the case of a greenfield site or a new design, you won't necessarily have all that information to hand. So you have to make assumptions in place, and you really want to try and make those assumptions as appropriate as possible, because you might miss something important otherwise and end up with a different result to what actually happens in reality.
And in terms of this particular instance with KO data, you use CFD analysis, but you also use digital twin technology. Now, I've heard quite a lot about it. I've read a bit about it. I'm not sure I fully understand it, but can you tell me where the sort of CFD stops and the digital twin starts, and what that brings to a project like that?
Yeah. It's an interesting question. For us, the digital twin was a natural extension of, or a natural name for what we're doing anyway. But CFD exists, or existed before the advent of the digital twin term, and digital twins exist without any CFD component. So a digital twin, I think, is ultimately just a computer model of a real life system. And I think the often cited example is spaceships. For some reason, I think NASA possibly coined the phrase. But yeah, so you have a model of either a system you're designing or a system that's in operation, and that model provides insight and analysis, and you can run real-time real-time monitoring and real-time analysis against that system. So that's a digital twin. The CFD part, as I was just saying, is the fluid dynamics. So that's actually breaking down what is airflow all around us, which is a continuous thing, and it's digitizing it into a computer model. So it's actually, I think you could argue that CFD is an abstract version of a digital twin anyway. It's a digital version of airflow. For us, the CFD component is integral to the model, because data centers by and large rely on airflow to cool their equipment. They rely on airflow to extract the heat, and it's the air in that space that really connects all the systems together physically. So we have to consider the CFD as part of our digital twin. The software itself can model, as I was saying, the control systems and the servers, the objects you'll find. It can model chilled water pipe work. It can model power connectivity and the power draw through the various components in the system. So the model itself is more than just CFD. It's a lot more than CFD. And as time goes on, that model's becoming more comprehensive, and it can be used to analyze different states of a room. So it can be used on an operational basis as well. But yeah, that's, I guess in a nutshell, that's how the two terms or the two technologies have combined. And we found that the digital twin terminology has helped us actually kind of connect with people, because they understand the digital twin, but CFD is possibly more of an unfamiliar concept. But when it's pointed out that they're actually one and the same, I think it helps people understand what it's doing.
And in terms, I mean, to me and potentially to yourself, it would seem surprising that people would still design a data center without using some kind of modeling. Is that the case, or are most people now, whether it's adapting an existing data center, reconfiguring it, do they do some modeling? Or obviously, as you mentioned, greenfield, it makes sense to sort of model it before you start, or are you surprised that some people still kind of do it on the back of a piece of paper, or think they know, they roughly know what's going to happen, so we'll give it a welly and see what happens?
Yeah, there's just had a lot of thoughts as you've been talking, so I hope to get them all. But I guess we've been gradually seeing business increase, and especially recently it's really ramped up. So there's lots and lots of interest in the CFD at the moment. We're extremely busy, and I know that people using our software to provide services similar to consultancy services similar to those that we offer are also very, very busy. So there's no doubt in my mind that the technology's kind of really taken a foothold. I mean, I guess from experience in making models over the years, we can see designs when we come across a new design from a new customer. We might be able to categorize it as one of those designs that's going to fall into this set of problems, or fall into that set of problems. So I suppose any experienced practitioner will have a similar gut feel when they see a design or when they create something. But these days, when you're looking at some of the higher power densities that are going on, that are being installed, there's very little wiggle room for error, and that error can be catastrophic, because the amount of heat that you'd be recycling if you weren't managing that waste heat properly. So yeah, we're I think in addition, it's not just a temperature problem, it's a pressure problem. So you've got hot air in a room, but because of the volumes of air being thrown throughout the space, you've also potentially got pressure issues, and you can end up with air being sucked the wrong way through cabinets because there's a low pressure zone because of the velocities of air at certain points in the room. So I think probably if you think about all of these technologies, they're ultimately used because we've got to that point where you can survive with hand calculations and you can get away with it. And we're now looking at higher performance where the margins are smaller, the error margins are smaller, and you've got to manage your design or create your design with more diligence and more precision. And I think if you look at any application of this, I often think in Formula One, it was when they started doing CFD, it was when they started making these advanced analyses that performance suddenly found a new kind of level, and that they were able to eke out extra stuff. And I think the industry, of course, and the whole world is looking at sustainability more now, and the environmental side of things is on everyone's mind. It's extremely important, and that again takes away some of that freedom to just turn the cooling up if you want to. And you can't do that at KO Data because they don't have any mechanical cooling. That was one of the principles of the design. So they were very keen to ensure that that design was robust before they committed to building it.
And in terms of the use back to CFD, just quickly, it clearly upfront design, configuration, whatever is very important. But in the KO Data example, I think it was also used, you know, to your point about more high density, there was a high performance computing. They wanted to install a supercomputer. So again, they were able to model and understand the impact or where and how to implement that project.
Yeah. So the NVIDIA equipment, I think it's safe to say the types of density we're looking at the moment are something like 15 kilowatts a rack. So maybe 10 years ago, in fact, even today, some facilities, you're still only looking at 3 or 4 kilowatts a rack. A few years ago, you wouldn't dare go above that. And now it's quite common to see really high density equipment. And I'm fairly sure that NVIDIA equipment can be installed in higher power densities than 15 kilowatts a rack. But yeah, obviously with that, the location within the space can make a difference to how well it performs. Like if you move it a bit left or a bit right. I mean, but it's I don't want to go into the detail, but little nuances in the design can make a difference between all of the equipment feeling okay, or some of the equipment not feeling okay. And obviously the aim is for everything in the room. And I think that's another thing to recognize. We're not looking to maintain an average condition that's acceptable. We need every single piece of equipment in that room to be sufficiently cooled. And that's where it becomes harder, because it's a blanket rule. Everything's got to be all right. So you need to make sure that your hotter spots are still no hotter than they should be, or no hotter than acceptable limits.
And just quickly on the free cooling front, because I mean, I know that's the sort of holy grail that if you just let nature take its course, and that's great, and it doesn't cost so much. But with technologies such as yourselves, is that a key to obtaining that kind of result? I mean, clearly there are other things, depending on potentially the location of the data center, how it's constructed. But is CFD quite an important part of making sure you get as much free cooling, or obviously in the case of KO, 100% free cooling?
Well, yeah, I mean, I guess the thing with free cooling is, as I was saying, you can't turn up, you haven't got chillers, you haven't got mechanical plants, so you can't turn up the cooling. So you're limited by what the environment's giving you, what the external environment's giving you. We have to make sure that site, or we wanted to make sure that site would work in worst case conditions. So the study was performed against, I think, ASHRAE worst case, or ASHRAE extreme temperatures, and humidities as well, because there's the evaporative element to the system. But still, ultimately, you have a hard limit of cooling that's available. And with that limit, you have to make sure that all of your equipment is okay. So you don't have that headroom. Again, that was the issue. So free cooling is obviously a major bonus in terms of efficiency. If you wanted to install the mechanical plant as well as a backup, then you're suddenly looking at a massive reduction in sustainability purely on the material usage, because you've suddenly got to install all of this equipment and maintain it just on the off chance that you might have to turn it on one hot day. So it's not, you don't really want to have that kit there. So there's that side of it. There's that capital use or capital expense side of things, which is a consideration, but also the fact that the free cooling is well, leaner, I guess, is a fair way of putting it, is a result of its efficiency, of its inherent efficiency. There are other ways to provide efficient cooling. So liquid cooling is obviously something that's becoming more and more considered. And again, that's something that I think we feel will always form part of a facility. You'll have an airflow or an air-cooled side of it, and you might have some liquid-cooled equipment as well, maybe the really high-density stuff. And again, that's another part of the Six Sigma model that we're building upon at the moment, so that you can integrate these aspects to the design. So I think we're going to be looking at different solutions as time goes on. But I think the key here is about wasted energy and reducing that wasted energy. And if you don't want to waste it, then you've got to be very precise and efficient up front. That's the important bit.
Okay, and maybe just in conclusion, a final thought to people who are looking at CFD stroke digital twin technology to do with, as I say, whether it's, I guess if you're lucky enough, you've got a nice green field and you can build the world's most sustainable whatever, but a lot of people, they got a legacy data center, so they've got to work with what they've already got. So in a nutshell, what to look out for when it comes to a CFD stroke digital twin solution, the sort of things to ask vendors.
Oh yeah, okay. What to look out for? I would say that I think it's important that you feel confident that the vendor is competent and understands your requirements. I think the number one thing to understand from any CFD analysis is the objective, the customer objective, because that really informs where the modelling effort should go. So I think if you assume that the software that you're using is capable, and it needs to be full comprehensive CFD software. So I think that's one thing to look out for. Is the software capable of modeling all of these different systems in unison, and is it accurate? But then also the provider and what they offer as a consultant, and how familiar they are with the data center space. I think you can extract quite a bit extra out of an existing site. We've proved that multiple times, where people feel that they can't put anything extra in a room, and then we'll create a CFD model of it, and just to have that 3D picture in front of you, and suddenly you can see, you'll from walking through the data center that it's hot in row L, and it's super cold in that corner, and then you suddenly see it in a model in front of you, and you can see why. You can see the air coming from one unit going to another unit. You can see where it picks up the heat, or why it remains cold, and people suddenly click. They're like, I understand it. And then with that confidence, they can reconfigure the space, or they might make a decision to deploy some extra cooling with the confidence that it really is the right option. It really is the right thing to do. But yeah, it just allows you to take away that guesswork. So I think, in terms of choosing a vendor, I just think find someone that you feel you can have a conversation with, and and explain to them what you want, and that they understand it.
Excellent. Well, it's been good to talk to you. So Alex, thanks very much indeed for your time. Appreciate it.
Thank you very much. Cheers.